All right, let's get started. Today is ninth session of the ML Scalability and Performance Reading Group. Today we're covering this paper, which is an important one called Reducing Activation, Recomputation in Large Transformer Models. This paper directly builds upon the Megatron-style tensor parallelism, which we looked at last week, or rather last session. And it's actually kind of what motivated me to choose this one this time is that it's this kind of combination of techniques they use here, tensor parallelism, as well as what we'll see they introduce, sequence parallelism and selective activation recomputation, has become fairly standard in some of the open source LLM implementations you'll see of tensor parallelism. So yeah, I think it's like an important one to understand. And so with that, we can go ahead and get started. So basically, starting in the beginning here, what they do is just remind us, like reintroduce tensor parallelism and pipeline parallelism, which are the kind of true forms of model parallelism, which are have been popularized at this time, and which they are trying to find ways to improve. So they note that with tensor parallelism, the trade-off is that there's more communication requirements, and so there typically only works well on small groups of tightly connected devices which have like a high bandwidth, low latency network link, such as NVLink between them. But as a result, you get smaller activations because we're actually partitioning the literal tensors, the weights in the layers, and so when you multiply your input activation by a smaller tensor, you get a smaller output activation. So it can reduce peak memory used during your training, and this allows you to fit larger models without hitting ohms. The other form, pipeline parallelism, a different form of model parallelism where we are partitioning the model vertically, right? Partitioning between layers and grouping the layers into stages and putting those stages onto devices. It actually, it does not reduce the size of the activations, right? Because we still have a full layer on the device. So when we do a pass through the layer, the computation is not sharded. We're doing a full layer times the full input activation. It's just that we've partitioned. We only have a few layers on the device, so that device will only hold a subset of the actual parameters in the optimizer states. So we do reduce the parameter and optimizer state storage, but we do not reduce the size of the activations. So these are kind of different trade-offs here. And then the other thing with pipeline parallelism is that unlike data parallelism, right, where the communication, the amount of data sent between devices scales with respect to the number of parameters, right, because we're doing like a full all reduce between all the gradients on all the devices for all the parameters because they're replicated across devices. The communication with pipeline parallelism scales with respect to the size of the output activations between layers at layer boundaries, because that's the only data that needs to be sent from stage 1 to stage 2, and then the output activations from stage 2 to stage 3, and so on. So that's just a very brief reminder of tensor parallelism and pipeline parallelism. Okay, so let's continue. And then they note here this other technique to to try to scale up to larger models where we start getting out of memory errors because of these huge activations, or activations tend to dominate the memory usage in very, very large models. One technique called full activation recomputation, or full AC, means that we basically, for all layers in the whole model, we only store the input activations to those layers. We do not store any of the intermediate activations that are needed to actually compute all the gradients. And then during the backward pass, we just use that input activation to recompute those intermediate activations as necessary so we can compute the gradients. So we're basically completely minimizing what we're actually storing during the forward pass. And that allows for more free memory so that we can scale up the model and train larger models. But they note there's a 30 to 40% execution time overhead when using full AC. So that's kind of what they're looking at here, right? So that's the remember the title of the paper, Reducing Activation Recomputation. So this overhead, they're wondering, do we really need, is there something else we can do? Can we avoid, recomputing like all the activations but still training these large models? Yeah, so with that, we can kind of move on. They do note here that other techniques to reduce peak memory usage, like CPU offloading, are orthogonal, and you can get even greater memory savings if you use those. Cool. So that's just kind of like a little review for the intro. Then for related work, um, yeah, they just basically it's kind of the same stuff. They talk about two forms of model parallelism, TP and pipeline parallelism. And let's see if there's anything worth covering here. Yeah, I think I already pretty much. Oh, okay. So yeah, I covered most of this, but one interesting thing here. So they do mention that there's this previous form of sequence parallelism suggested in 9, the reference 9. And if you look, reference 9 is actually what we covered in a prior session on ring attention. This is sequence parallelism, long sequence training from a systems perspective. So what this paper was about was it basically introduces the entire concept of ring attention, and where you partition along the sequence dimension, like rotate the K and V's around, but keep the Q's fixed to the device to compute the attention outputs. They somewhat confusingly are going to call their this is kind of annoying to me. They're going to call their technique sequence parallelism as well, but it works completely differently than that form of sequence parallelism. So just keep that in mind. I wish they used a different term, but where were we? Yeah, so what they say is that form of sequence parallelism, where the activations are partitioned along the sequence dimension, it requires the parameters and optimizer states to be replicated on all the devices, which makes it not suitable for large model training. So it does, the activations will result in, those will be partitioned, kind of like in tensor parallelism, but the parameters and optimizer state are not. So it's, that's a limitation. It will not be suitable for large model training. Another limitation they don't mention is that the communication overhead is actually, some of it is exposed, like not fully overlapped with the computation. So there's, that limits the scalability as well. And that was only fixed, if we remember from our ring attention session, by combining it with blockwise transformers. And then that's how the researchers from Berkeley came up with what is called, ring attention colloquially today, combining sequence parallelism as described in this paper with blockwise transformers, which fuse in the feed forward and residual layer into the actual flash attention computation. So it's like all one blocked computation, and you are basically fusing in more compute, which allows you to fully overlap that ring style communication overhead of passing the K's and V's around. Thus, you can kind of scale up with quote unquote zero overhead, at least in theory. But yeah, this paper is before that, but I just wanted to remind everybody kind of the context that we've, it's always nice when we've already covered some of the stuff they're talking about here in the related work. So that was just a brief reminder about that. And then, yeah, now they say in this paper they present a new technique which leverages the advantages of both tensor parallelism and sequence parallelism without any of the previous approach's shortcomings. And it also reduces the activation memory significantly without any additional compute. This isn't actually true. There's some additional compute, we'll see, but it's pretty minimal. So yeah, they're going to reduce activation memory required with only a small amount of extra compute, which is not the case for their baseline they're comparing to, which is full activation checkpointing, which does significantly reduce activation memory required, but at the cost of a ton of extra compute, 30 to 40%, they said. So moving on, this is just a brief review of transformer architecture. We can skip that. Activation memory, this is where they basically quantify the exact, like an algebraic expression which quantifies the amount of activation memory required in bytes for a given model. If you're storing all the activations, all the intermediate activations, like everything, performing no kind of activation checkpointing. And this is kind of the baseline, which they will refer to in terms of memory usage. So I know this is maybe not super. This is like a little bit boring, but I think it's we should just quickly go through this because this is kind of important. So to understand, because they're going to constantly be referring and revising this equation in this paper with each additional optimization they apply. So let's understand what these terms are. So basically they're saying first there's attention block, MLP, and layer norm, right? Those are what they're going to look at. And for the attention block, let's start actually here for the Q, K, and V projections in terms of what we need to store in order to do the backward pass later. We're going to be storing the input activations, which is the batch for each batch. We have the sequence and then the hidden dimension. So B times S times H, and then 2 bytes per sequence, because this is assuming 16-byte floating point format. So that's probably B of 16. And so that's for the Q, K, and V projections. Then for the Q, K transpose, the raw attention scores, that's going to be storing both Q and K, right? Because we need to take the gradient with respect to Q, gradient with respect to K. So we're going to need both, and basically that's going to be 2 times the actual size of Q and K, which is going to be it's 2 bytes per element, and then 2 SBH. So we get 4 SBH. Then for the softmax, this is going to be A is attention heads, S squared, if you remember, the attention, the raw attention scores that are passed into softmax, the inputs, that will be S squared, right? That's like famously why flash attention was invented, right? The huge S squared memory requirement here, and then times B, right? So 2 bytes per parameter times these values. Then for dropout, we only need the AS squared B because it's only 1 byte per parameter, because the dropout mask is just like a Boolean mask, like it's just like 1 or 0 basically. So we can use the lower precision. We don't need like 16 or 32 bits. Attention over values. This is where we multiply the the softmax attention scores that are probability distributions, row-wise softmax on those by our V projection. So for that, we need to store the dropout, which we already talked about here. Or sorry, it's 2 bytes times, it's the same as the input here. And then the values, which are 2 SBH, which again, same thing with like Q and K, 2 SBH. And therefore, you just need this sum. And then finally, now we're at the end of the attention layer, right? We need to go through our output projection, right? There's like a 1 linear layer afterwards, our output projection. That is going to, we need to store the input activations, which are 2 SBH, right? For each batch, each sequence, each hidden dimension, there's 2 bytes. And then the attention dropout mask, which is just 1 byte per each of those, so just SBH. So finally, when we add up all of these, we get this, 11 of the SBH terms, and then 5 for the AS squared. These are like the attention terms, right? From here, from the softmax dropout, and the attention with the values. So these are the attention specific terms. So that's the full amounts required so far. Then after the attention block, we have MLP, which remember is projecting from embedding dimension to hidden dimension. Or sorry, it goes to embedding dimension times 4 times the hidden dimension, and then it goes back from 4 times the hidden dimension back to the hidden dimension. So it just projects up, does a Gelu, and then projects back down to the original dimension, right? So 2 SBH, that's the original input coming out of the attention layer, right? 2 SBH. Then 8 SBH is going to be the input to the second linear layer, right? Because we've projected up. It's 4 times as large now along that dimension, the hidden dimension. It's like 4 times the hidden dimension. And then the Gelu in between them, it's still that large one, right? It's still that large one, and so we're going to need to save that one, right? So that's 8, 8, and 2. And then finally, of course, the dropout mask, which is just 1 byte per element, and that's SBH. So that brings 19, okay? And then finally, last one, almost done, the layer norm. It just, you store its input size, or your input, just like everything else, 2 SBH, and then 4 SBH. Oh, sorry, it's 2 SBH and then 2 bytes per element, so that brings it to 4 SBH. So finally, we have this important expression here, which will be referenced many times and built upon, where we get, basically this right side has to do with the attention related activations, and this left side is everything else, MLP, layer norm, etc., and the common factor of SBH. Okay, thanks everybody for sticking with me through that. I know that was like kind of not super interesting, but we're only going to look at this paper once. So I think it's nice to make sure we have a complete understanding of where these terms are coming from and not just kind of like scroll past it. Cool. Now what we're going to do is we're going to see how does tensor parallelism affect, so this is directly referencing the form of tensor parallelism from the Megatron LM paper, right? You remember last time if you were here, there's the F operator, which is like no operation in the forward pass, and then it does an all reduce in the backward pass, and F bar is the conjugate. So after this tensor parallel region, we have to all reduce the output, right? And in fact, let's just like briefly remember in case you weren't here or if it's just you need a reminder. You remember, so like here's an example of the tensor parallel region of the MLP layer, right? You can see here that we have, partitioned our weights, right? So this is this X right here is our input activations. See, that's how it's not partitioned. That's what they mean by F in the forward pass is no operation. It's like replicated on all the other devices. We have the full uncharted activation. The weights are partitioned column-wise. So we get these column-wise output activations of the first linear layer, go through our Gay-Lou nonlinearity, and we still have the same shapes, partitioned the same way. Then we have our row-wise partition of our second linear layer that projects back down to the original dimension. And then we can do these computations individually on each device, right? Here's this one, we get this output shape, and then on device 2, we have this matmul locally, and we get this output shape. And then now, here's the F bar operator, right? The all reduce. We have to all reduce in the original vanilla TP as described in Megatron. We all reduce, and now we go through dropout the dropout computation is replicated on each device. There's no partitioning here. And this is what is going to change in this paper. So let's go back to the paper. So here is the diagram, right? F and F bar we just looked at. And it's the same thing for attention and MLP. Those MLP and attention are the two regions which are using tensor parallel. Everything else, dropout, layer norm, residual, is using nothing. It's just replicated. The computation is duplicated. It's like wasted. So let's continue now. So what they're saying now, they're just basically setting the baseline. Okay, now going from the full activations that we're not doing anything fancy, we have this expression for how much memory we'll need. Now if we apply tensor parallel, we can divide the 24 from that 34 right here. 24 of those are divided by T. So 24 SBH are divided by the tensor parallel group size, right? And let's not, maybe this isn't interesting, but I think it's important. Let's look exactly why that is. So basically, if we go through these and see which of these in tensor parallelism are actually partitioned, which of these activations are partitioned and which are not, which are replicated. So if we look at the layer norm, if we remember looking at our diagram, it is not subject to tensor parallel. So it will not be included in the 24 that we're dividing, that is being divided by the tensor parallel group, right? So we can ignore this. MLP. The MLP inputs, the original, looking at the MLP inputs here, so going back to our diagram, those are not partitioned, right? Here it is. It is not partitioned, so it is not subject to, we're not getting any memory activation reduction dividing by the tensor group size. It's not subject to the 24. However, the actual linear layers themselves, right? So these, A1 and A2, that's going to be, the activations here, X1 and XA1 and XA2, those are partitioned, see, by the tensor parallel group size, which is 2 in this diagram, right? So that will be included. So that will be the 8 SBH, right? Because that's the 2 SBH is the original input to the MLP. 8 SBH is the intermediate activation going into the second layer. That's this. So 8, we're trying to get to a total of 24 here. We're trying to figure out where did this number come from? How are they just stating this arbitrarily? They don't show their work, so let's figure it out. 8 SBH will be partitioned, and then this 8 SBH, the Gay-Lou, right? That's also on this diagram, right? We're applying Gay-Lou here. That's also partitioned in tensor parallel. So that's 16. 8 plus 8 is 16. Okay. Now let's keep going. Now let's look at attention. For Q, K, and V, for the projections, are those partitioned? Let's go to our diagram. So for the projections, yes, Q, K, and V activations, these are partitioned. So in the paper they do it column-wise, but the inputs to those are not partitioned, right? So let's read this carefully. They only store their shared input with 2 BSH, right? So this is not partitioned, right? And so let's move on to the next one. Q and K, they are partitioned, right? They store Q and K, but those are partitioned, right? Q, K. So then we were at 8 plus 8 is 16. So then we add here 4 BSH, and that brings 16 plus 4 is 20, right? And then let's keep going. Softmax, yeah, these are not, we're only looking for BSHs, right? Because it's 24 BSH over T. I was a little bit confused why they're not mentioning the softmax. Oh, okay, never mind. Yeah, because softmax, they don't, yeah, here, this is not partitioned, that's why. So the Q and K, right, we go through softmax, but the actual softmax is not partitioned. You see, we have the same size on both devices. I hope this is making sense. It's the same size on both devices. It's not partitioned, right? The values are partitioned, and the output activations, right here, Y1 and Y2, are partitioned. So if we look at attention over values, the 2BSH, right, values, 2BSH, those are partitioned. So we were at 28 plus 8 plus 4 plus 2, that's 22 now, right? And then finally, where are the other two coming from the 24? Finally, the output, so we're at this point in the diagram, right? We've looked at the input, we looked at the Qs, the inputs were not sharded, the Qs and Ks are sharded, the values are sharded, the softmaxes were not sharded, the values are sharded. Now let's find the last two BSH here. The input activations for the linear projection. In this case, for vanilla tensor parallel, they are sharded. Here's the linear output, right? Here's the input activations. Because of the way we've partitioned the prior stages of this layer, of this attention computation, they are indeed partitioned. So that 22 plus 2 is now 24. And we divide all that by the tensor parallel group size to get 24 over T. So that's how they arrived at this this value. Is everybody with me so far? I know that was kind of a lot. It's kind of hard to verbally describe math. Did that make sense? At least at a high level? Anybody alive out there? Okay, I'll take that as it makes sense. So let's keep going. So now we have a concrete understanding of how they arrived at this specific formulation for how much activation per memory is required per layer. So now we can finally get to the fun part, which is the new techniques they introduced in this paper. So how can we reduce this activation memory even further? Well, basically what they note is that these regions in this diagram, the dropout, layer norm, etc., are not being partitioned in any way. So we're duplicating that memory across devices. So they took a look at that and they realized, this is the key part here in the blue, we noticed that the tensor parallel regions of a transformer layer, the operations are independent, we noticed that in the non-tensor parallel regions of the transformer layers, the operations are independent along the sequence dimension. This characteristic allows us to partition these regions across the sequence dimension S. That reduces the memory required for the activations. So the non-tensor parallel regions were like I said, dropout and layer norm, right? And what they're saying is that basically, unlike attention, for example, there's no, within the sequence dimension, there's no interaction between the vector, representing one token for one element in the sequence and another token vector in the sequence. And when you go through the layer norm or the dropout, right, these are applied independently along the sequence dimension. Right? So if we think about layer norm, what is it doing? It is normalizing along the feature dimension, which in this case is the hidden dimension, the vector for each token that represents it in the embedding space, right? So, it's not like, say, batch norm, where we are normalizing across the batch dimension, which would cross these boundaries, but layer norm is going along the feature dimension. So it's applied individually to each vector along the sequence, right? So it can go, what they notice is that we can partition the output of these tensor parallel regions, both the attention layer and the MLP, we can partition it across the sequence dimension and then do layer norm individually across the devices, and the math still works, basically. But this is kind of interesting because you might think, well, this seems like kind of obvious. Like, why didn't the original authors of Megatron do this? It's actually a little subtle why this is even beneficial. Because let's think about the collectives, the communication overhead that's going to be required to employ such a strategy. In the input to the tensor parallel region now, like the MLP, for example, the input activations, if we don't do anything, are now partitioned along the sequence dimension, right? And that's a problem, right? If we're going from, say, layer norm to self-attention, we cannot partition across the sequence dimension, at least not, just in regular multi-head attention, right? So, we basically what we need to do is an all gather here, right? And that's what they say. This new G operator, rather than F, which is in the tensor parallel, right? This was F. They're now transforming this from F and F bar to G and G bar. So G is going to all gather before the self-attention layer, right? So after these sequence parallel regions drop out layer norm, we'll all gather the results, and then we'll apply tensor parallelism, right? So we'll all gather, and then we'll have our same tensor parallel region where we go through this, this diagram like we showed, partitioning the Q's and K's column-wise across devices and so on. And then G bar, rather, is reduce scatter instead of all reduce, right? Because previously, remember, in these tensor parallel regions, afterwards we would do all reduce before going into like dropout and then layer norm, right? But here, what we need, since this is going to be a sequence parallel region, we need the inputs to be partitioned along the sequence dimension. So the most efficient way to do this is to use a reduce scatter. You could do like all reduce and then like a scatter, but that's two separate collectives, and it's not like the nickel library by NVIDIA actually offers a specific collective. It's one of the fundamental collectives, and it's called reduce scatter, and it will do what it sounds like. It reduces, and then it reduces the given tensors across the devices and scatters along some scatter dimension that you specify, which in this case is the sequence dimension, right? So that way we get our reduced outputs like we need mathematically, right, as we described last week, but we also get our scatter so that we can perform the next layer along the sequence dimension. And why I say it's unclear that this is favorable, because now, if you remember, let's look at this. The previous formulation, just pure tensor parallelism, it required no collective entering the tensor parallel region and only one all reduce after the tensor parallel region, right? So that's one tensor parallel region after the, one all reduce after the attention layer, and then one all reduce after the MLP for the forward pass. Then for the backward pass, it's the same, but just different locations. You have an all reduce after you go through the MLP backwards here, then you have an all reduce after you go through the attention backwards here. Okay, so that's 4 all reduces per forward backward pass per transformer layer. Okay, cool. Now, what is this? How many collectives do we have here? Well, this is now one all gather, one reduce scatter for the tensor parallel region, then another all gather, then another reduce scatter. So that's 4 just forward for one layer, 4 collectives, and then backwards we're going to do the same collectives but just swapped inverse, right? So it'll be, 4 forwards and 4 backwards. So on its face, it would look like double the amount of collectives, right? And so on its face, you might say, and they do say in the paper, they're like, well, this is, it's unclear if this is actually favorable because there's more collectives, so more communication overhead. Maybe this will slow down training. But in fact, the implementation of ring all reduce, which is what's used in the vanilla tensor parallel, is actually under the hood composed of a reduce scatter followed by an all gather. So theoretically, if you, instead of doing an all reduce, which is what's done in tensor parallel, if you instead do you're basically just decomposing the all reduce. You're decomposing it into a reduce scatter and an all gather. I mean, not just in terms of the communication overhead, you're just decomposing it into two collectives, which overall should have the same amount of communication overhead, right? So that's an interesting kind of under the hood implementation detail that these authors were aware of that allowed them to, um, you know, figure out this approach, basically. Cool. So hopefully that makes sense, the theoretical justification for why this should work now, both mathematically and then also from a communication overhead perspective. Now here's like just this math of what this should look like now. In the blue, this is the same tensor parallel strategy as described in Megatron, no changes there. In the green, if we just go through, like let's say our inputs, we're going through layer norm, those will be partitioned along the sequence dimension, right? So we're doing sequence parallelism in the layer norm layer, and our outputs will be sharded across the sequence dimension. Then, like I mentioned, we're going to have to all gather along the sequence dimension here, and to get our full Y output activation, in order to go into the tensor parallel region. And here's where we have, just like in our, if we look at, this is the MLP, right? So if we look at our MLP diagram, just to match things up and make sure that we are convinced that this is correct, the input activations for the MLP layer are not sharded. Here they are, full matrix, right? This is what is described in Megatron. And here we can see they have the full unsharded activations. Y, they just call it Y here. That's multiplied by our A matrix, our first linear layer weight, which is partitioned column-wise, which is what we had in Megatron, right? Partitioned column-wise. And then those are applied GALU individually, which is what we did here. Then we do, now this output is partitioned column-wise still, as we show here. They call it ZH instead of ZC, I think because we're projecting to the hidden dimension. So A is, it's the weights, so we would just say it's partitioned column-wise, but the activations are projected up to the hidden dimension. So column-wise, I believe what they're saying is that column-wise, the notation for it would be partitioned along the hidden dimension. That's how they make it clear. And then finally, just like in a second, we went through GALU, we're going to go through our second linear layer here. This one's B matrix is partitioned row-wise, just like in Megatron, right? B is partitioned row-wise, like here. And we now have our W1 and W2 activations, which are here. And then here's where the difference is. Again, we do reduce scatter along the sequence dimension. So rather than doing all reduce, we do a reduce scatter here, and then apply dropout to them individually along when they're partitioned along the sequence dimension, and we have outputs which are partitioned along the sequence dimension. And then this would all start over, right? We go into the next layer, we go into the next layer norm, right? This is still along the sequence dimension, and then we would all gather and then go into the, this at some point we'd have like an attention layer and so on. So yeah, that's the new math describing this. Here's where they describe, what I just already talked about, the number of collectives, 4 all gathers and 4 reduced scatters, and the 4 backward, and how it's equivalent because the implementation of all reduce, the ring-based algorithm, is actually just composed of an all gather, a reduced scatter followed by an all gather, so it should be equivalent. And then now, I guess one thing we should mention here too. One unintuitive thing they do, or it's not obvious from the math, is they don't store the entire all-gathered Y tensor for the backward pass. This makes sense because they're trying to reduce peak memory, right? And so we don't want to store the full thing if we don't have to. So they store only the shard that device is responsible for, but then they perform an all-gather during the backward pass when it's needed. But what they do is they overlap that communication with the computation required to calculate the gradients with respect to Y. So that makes sense because when you're calculating the gradient with respect to Y, it's going to be, some other, you're going to need some other values, not the full Y matrix itself, right? Because, if you think of like W equals Y matmul X, the derivative you're going to compute the gradient of the loss with respect to Y as the gradient of the loss with respect to W, your output, and multiply that times X, which is what you matmul by Y, right? And you'll get your derivative of your loss with respect to Y. Hopefully that makes sense. Maybe I should have written some of this down. Like verbally describing math is maybe not the best way to communicate it. But anyways, now they provide this new formula here, and I've highlighted the new difference. The difference is now the portions that were not partitioned before are now partitioned, right? This was from the layer norm and dropout and stuff. This is now partitioned over the T dimension, the tensor parallel group. So this reduces our activation memory for this portion by a factor of T. Cool. See, is everybody still here? Okay. If anybody has any questions or comments, please chime in. I'll pause for a second before we keep moving. Anything at all can be. No such thing as dumb questions, only dumb answers by me. So you can put me in the hot seat. Okay. Well, moving on then to pipeline parallelism. Basically, another fun fact. So they're basically talking about how pipeline parallelism, which is often combined with tensor parallelism for very large models, how it affects this formulation of the total activation memory required. And they are specifically talking about the 1F1B pipeline schedule developed in PipeDream. Remember, everybody who was here at the pipeline parallelism session where we talked about gpipe, PipeDream, and zero bubble. PipeDream was the one with like async pipeline parallelism with the 1F1B, one forward, one backward steady state, where they also have that cool like heuristic-based algorithm to decide which stages are slowest, basically, like how much computation is required, and they can then replicate that stage with data parallelism so that we can concurrently process more micro batches to bring its total execution time for the n micro batches, make it roughly equal with other faster stages of the pipeline to keep like a uniform execution time, or as close to uniform as possible between the stages, so the whole pipeline runs smoothly and we minimize idle time on each stage, on the devices on each stage. Because what we don't want is some one stage that takes forever with a bunch of backed up like a clogged pipeline, basically like it's running at full capacity 100% of the time, but the other stages that are faster, there's a bunch of idle time as it waits for this next stage to complete. So that's kind of what was going on in PipeDream at a very high level. There's also okay, I closed it, but I had a little diagram. But anyways, they just say, for each stage, it contains L over P layers, where P is the number of microbatches. So the first stage must store, P times L over P. So basically L layers worth of activations regardless of the pipeline parallel size. So they introduce this L term, basically, to our previous formula that we have up here, if we're combining with pipeline parallelism, which they are. Cool. And then now this section, not that important. This is just like their long-winded way of saying, basically equation 5, this equation, captures the vast majority of total activation memory required, but technically it leaves some stuff out, and if you include that other stuff, it only results in 0.01% extra total activation memory, so they keep the simplified formula here, because it's like virtually identical. Now, finally, selective activation recomputation, or SAC. Basically here, what they're going to do is they're going to try to intelligently choose which layers we recompute and which ones we store the full computations for, or sorry, the full activations for. And what they're using to determine that is how much computation is required for that layer to recompute it, right? And then how much activation memory are we saving by recomputing, right? And we want to find a favorable trade-off, right? So as their baseline here, they're looking at to just full activation recomputation has an extra 30 to 40% computational time overhead, right? So what they do is look at some of the layers and try to find layers where, like or activations where you would by checkpointing, you would save a bunch of memory because the activations are very large, but actually to recompute them requires very little computation, right? It's not like a very compute-heavy operation. So Here, if we just read what it says instead of checkpointing and recomputing full transformer layers, we propose to checkpoint and recompute only parts of each transformer layer that take up a considerable amount of memory but are not computationally expensive to recompute, aka selective activation recomputation, which is what I was just explaining. So what they're going to do now is they kind of look at the attention layer specifically and they say, okay, the term 5ASH in equation 5, which is our it's this one basically. It's our where is it? Tensor parallel. It's okay. Well, I can scroll further. It's this one right here. It's the equation representing the total activation memory required with both tensor parallelism and pipeline parallelism applied. And what they say is that 5ASH, that's not a constant. That will grow much larger for large models. A is attention heads, S is max sequence length, H is hidden dimension. And what they're saying is for certain, these are this factor they are multiplying in equation H or 5, I mean, by SBHL over T. That is not a constant, right? So it's due to the attention layer specifically. 34 is from everything else. So they're going that will be the largest impact on activation memory if we find ways to not store those, basically. So let's look at them. They say for these QK for these attention operations like QK transpose, softmax dropout, and attention over V. These operations have large input sizes and thus large activations, so lots of activation memory required, but the number of flops per input is very low arithmetic intensity. So the rest of the transformer layer is just the 34, the static or fixed constant there, or it's not a constant, it's a constant factor. You're multiplying by the BSH over T. But so what they're saying is for very large models where this term 5AS over H, which is the activation memory factor that we're using to determine how much activation memory is used in the attention layers, if that's much greater than 34, which is everything else besides the attention layers, if you checkpoint and recompute that part, the attention layers, you'll end up storing less than half of the activation. So you'll end up saving most of the activation memory that was used. You'll end up dropping, which is great, right? We're drastically reducing our activation memory required, and only have a modest cost to recompute those that aren't stored because, as they mentioned, the number of floating point operations per input element in these layers is actually very low. It's really like, attention, there's some mammals, but the like softmax and these things, those are not as, flop heavy, but require a huge amount of memory, right? This is not talking about flash attention or any memory efficient attention. This is just vanilla multi-head attention. So, and then they show this is in fact the case for large models. Like this checkpointing these is beneficial for large models. So for GPT-3, they multiply out their number of attention heads, max sequence length, and head dimension with this expression, and they get 80. And 80 is indeed much greater than 34. So that indicates that we will be reducing the majority of our activation memory if we don't store these activations and instead recompute them. Okay, so memory-wise, that's good. And they say, and they look at this other model too and show the same thing, another large model. And what they show is that by selectively doing activation checkpointing on those layers, you save 65 to 70% of the required memory, and it introduces only 2.7% and 1.6% for each model respectively flops. So it's very little increase in flops to recompute these, but you're saving a huge amount in your peak activation memory. So this seems like a very favorable trade-off, right? So using this, if we decide, okay, we're going to use this strategy, we're going to use selective activation checkpointing to checkpoint only these layers in the attention, then your total required memory is reduced to this expression, right? Which is better than equation 5, which we're looking at here. Okay. And let's see. Yeah, then they talk about a new equation basically allows the activation recomputation. This SAC strategy allows the required activation memory to scale linearly with sequence length and be independent of attention heads. This used to not be the case, right? I believe it scaled actually quadratically with sequence length because here there's only one S, right? But previously, there's an S in the outer term here, and then there's an S in the inner term here. So it's S squared, which is like famously why attention is so memory hungry, right? S squared scales quadratically with sequence length. Um, yeah, and then they talk about the pipeline parallelism section here. I found all the pipeline parallelism stuff in this paper kind of like not as clear as the other sections, but we'll try to go through it here. They say even though a given device only has L, the number of layers, or L divided by P layers, right? Your total number of layers divided by your pipeline stages. The first stage must still store an equivalent of L layers of activations, since it must store activations for P microbatches to keep the pipeline pressurized. So what this is talking about, here, I'll find a diagram just to be clear here. Here, remember, so the first stage, GPU1, you see the blue is forward pass, the green is backward pass. For each forward pass, right, for each of these microbatches, we are having to store those activations, at least the ones that we choose to store, because we're not going to get the chance to do a backward pass for a while, and we can only start discarding those activations once we have performed the backward pass and we no longer need that activation. Because the only reason we're storing it is so that we can perform the backward pass and compute the gradients, right? So it has to store all of them. Whereas versus look at the very last stage, it immediately goes into one forward, one backward steady state, meaning after the first microbatch comes through, we immediately do backward and can discard that blue activation, right? Do forward for 2, and then backward for 2 immediately. We don't have to store very much, so it's a non-uniform amount of activation memory required across the devices, or across the stages. And this is necessary, though, to keep the pipeline pressurized, so to speak, to keep it full. We have to, some of these early stages have to hold more microbatch activations in order to keep the pipeline full once we reach a one forward, one backward steady state. They say an additional technique that can be employed to reduce the recomputation cost in this case is to store all the activations for as many microbatches as possible, given device memory, or do full or selective recomputation for the rest. Okay, in practice, we find that applying sequence parallelism and selective activation computation, the recomputation overhead is small enough. This additional technique provides various modest improvement. Okay, so like not much change basically is my understanding. It wasn't that big of a deal. Evaluations. We'll go through this quickly. Basically, they just, set up some experiments here using models of various sizes, and they measure memory usage and execution time and iteration time. So individually, sequence parallelism and then SAC cut the memory requirement in half, but if you combine them, you get a 5x reduction. So under 20% of your previous memory requirement if you're not doing any kind of AC, no AC, right? So that's really good. I guess is all there is to say. Then as far as execution time per layer, they basically are comparing baseline with no recompute, just storing everything, and then applying sequence parallelism. And you get a bunch of peak memory savings, but there is some overhead. Wait, negative overhead. So I guess actually it's faster. I guess is what they're saying there. Yeah, it is faster. Baseline with recompute and then selective recompute, right? That's our SAC. And so, okay, so basically what they're saying here is like looking at the full, for this section, they're actually referencing full AC as their baseline because this is execution time, right? And they say in order to train these very large, they go up to 1 trillion parameter models in this paper. To do this before, the only way to fit these models and have them not hit ohms from activations during training was to do full activation checkpointing, full AC. Um, Basically recompute everything, store as little as possible, and that's how they did it. But that has a 39% overhead in your combined forward-backward execution time. But when they combine selective activation checkpointing and sequence parallelism, it's now only 4% overhead. So there is some, it is a little bit slower still, 4% slower, but you get 5x memory savings, under 20% of your peak memory before. So this is, very favorable trade-off. And then iteration time, same thing here. They are now comparing using the baseline of full AC, right, full recomputation. And as you might expect, you get higher throughput because we're recomputing less stuff, right? Because by using sequence parallelism and selective AC, we are, reducing the amount of stuff we need to recompute, right? Because we already reduced our peak memory using sequence parallelism and SAC, so we, can recompute fewer things, and we get higher throughput, basically, much higher throughput, increased throughput around 30%, which is really good. And that's the paper. That is it. Yeah, this is a very important one. I guess one thing I can show really quick is you can see that this, I'm pretty sure, like, well, I noticed this when I was looking at this, and that's what kind of got me interested in doing this paper. I'll just do it manually. So if you look at Torch Titan, again, this is a PyTorch native library for large model training, aka like reference implementation of various model architectures and the corresponding code needed to like parallelize them and so on. It's the official PyTorch one. So if you go to the actual models, so we'll look at Llama. This is Llama 3. And if you look at how they parallelize it, there's different options. And specifically in the tensor parallel, so here is where they, if you choose to apply TP, I hope everyone can see this. If you choose to apply TP, then if we look at the apply TP function, what is it doing? Well, what do you know? Inputs are replicated. We talked about this in the Megatron paper. Outputs are sharded column-wise for the embeddings, right? We talked about this previously, but we won't, to explain all this would take a long time. This was like one of the more confusing parts, if you remember, the input and output embeddings. But there, if anyone's interested, I do cover this in the diagram here. As you can see, it's somewhat involved. But these are available on the GitHub for this reading group, if you want to go over it. But the key part here is, look, for the norms, which would be like your layer norm or your RMS norm or whatever, sequence parallel. So see it says parallelize the norm layer over the sequence dimension. I'm actually not clear. I wonder if it says the root norm layer. I mean the root norm, like it's only the first one? That wouldn't make sense. I'm pretty sure that this is for each transformer layer, the norm is parallelized over the sequence dimension. Because they even say in, if you look at this GitHub issue, right, which is asking why we parallelize or partition the embeddings, right, the input embeddings column-wise, as shown here, right, across the vocab dimension. Very confusing, right? Because now each device only has a subset of the actual embeddings in the lookup table. So it's kind of confusing, which again, I explain in the diagram here. We won't cover it now because it'll take a while, but if you're interested in how that works, there's links to the relevant code and some explanations. But basically, in this answer, he said, if the next layer is partitioned across the sequence dimension, then it would require a reduce scatter beforehand, which is exactly what we talked about in this paper today, right? They do a reduce scatter before, they do a reduce scatter here, this G bar operator, reduce scatter on the tensor parallel region before entering the sequence parallel region, right? So I wanted to understand what he was talking about here, why it's reduced scatter and blah blah. And this paper, I think is like essentially what they're implementing. Maybe not like exactly, but I don't know. It seems to align with what is described in this paper. Yeah, so very cool stuff. As you can see, this is like very relevant in the real world and modern LM parallelization implementations and strategies. It's still very relevant. So a very important paper to cover today. Does anybody have any comments or questions before we wrap up? I can stop sharing my screen. No comments or questions. Okay, my explanation must have been amazing. Just everything crystal clear. Um, cool. Yeah. Well, in that case, I will go ahead and stop the recording. Appreciate everybody joining. I hope everybody got a lot out of this. I got a ton out of this. For next time, I'm hoping to do a different paper, which I'll post in the chat, but it's on async TP, so async tensor parallelism. This is a highly technical area, so I'm pretty excited to cover it and get a very concrete understanding. Um, and it's very actually relevant to stuff I'm working on at my job right now, and basically, you know, implementing various, support for various like quantization techniques and so on in the PyTorch async tensor parallel implementation. So I've been getting my hands dirty with that, and you know, so I thought it'd be useful to actually look at the paper and really get the foundational knowledge that informed the implementation I've been expanding. And so yeah, it'd be a cool session because I think we can both cover the paper and we can actually look at the PyTorch code that implements it, which does graph manipulation in the inductor. So like in the PyTorch compiler, basically the inductor backend, which is the part of the PyTorch compiler stack that will basically do like graph manipulation from the uh, like Torch Dynamo will do graph capture, and then it will go through for the forward pass. Then we'll do the AOT autograd part of the compiler stack, which will then compute the graph for the backward pass. Then we'll go through the partitioner, which will try to do some optimizations in like a sort of like a min-max problem, trying to like minimize like activation memory required and maximize like execution speed or something of that nature. I don't know quite the details, but and then finally the inductor backend will do some post grad passes um, on the graph to do some extra optimizations, and one of those is async TP, and it will fuse various all-gather matmols and matmol reduced scatters into one single node in the graph, so to speak, and leverage something called the symmetric memory APIs to basically implement these kind of like decomposed versions of tensor parallel, where instead of doing using these predefined collectives like all reduce and just having that be a full blocking collective, it can decompose them into these point-to-point, individual point-to-point communications, and decompose the computation as well into like smaller matmols, and have this kind of pipelined approach that ends up having resulting in a speed up compared to vanilla tensor parallel. Um, yeah, hopefully that made sense and gives you a preview of what that topic will cover. And yeah, I'll post the paper in the chat. And yeah, I guess see everybody next time.
So wait,
What?
is that so? Does this does this have like a longer runtime than like because the baseline with recomputes like a 39% higher longer runtime, right?
For the paper we looked at today, it has a slightly, where's the paper? It has a slightly 4% longer or 4% computational overhead compared to the baseline of storing everything, but it has a much lower overhead, like shorter runtime compared to doing full AC, which is full activation recomputation in the backward pass. So it's faster, basically.
Selective recompute.
Yeah, using selective recompute and sequence parallelism together, we get a 5x decrease in peak memory usage for activations, anyways, and then a significantly higher throughput. So 30% higher throughput is showed here, which is because, or sorry, it's 30% higher throughput compared to. So it's kind of they're doing two different. They're a little bit tricky. They're using two different baselines. For the peak memory usage, the baseline is not recomputing anything, just storing everything. And from that baseline, you get a 5x lower peak memory. But for the compute, they're using the baseline of recomputing everything, full AC.
Recompute.
Yeah, and from that, we get a significantly lower overhead and get a 30% higher throughut
But
overall.
with the selective recompute, there's like 3% or higher, more computations, right?
Yeah, there's 4% higher overhead compared to not recomputing anything, but much lower. Like if you just did full recompute, it's 39% overhead. So they just chose to recompute the layers that require very few flops, but use a lot of activation memory. And so you get a very favorable trade-off in reducing peak memory, but only barely increasing your compute.
I sorry, I missed. Was there a ratio of the flops to memory activation memory that they used for deciding the selective recomputation?
Yeah, it was right here. Where's the section? Basically, they looked at they just so one so okay, to answer your question directly, yeah, they use this ratio of 5 AS over H, which is 5 times activation or sorry, attention heads times max sequence length divided by hidden dimension, which is from our equation up here. It's the amount of activation. It's the constant. It's the factor that we're going to multiply by this full term, SBHL over T, as the model increases, like number of attention heads increases, sequence length increases, hidden dimension increases, the peak activation memory required for the attention layers will increase by this much, right? And in contrast, the whole rest of the model is only a constant, right? So even if the number of attention heads increases, it's a 34. So they looked at
Yeah.
my understanding is they looked at the 5 ASH and said that in cases for models where for very large models where 5 ASH is greater than 34, then it's favorable to like you'll basically save more memory. You'll save over 50% of your activation memory by not storing these activations for the attention layers. And this is even more favorable because the specific number of flops required to compute those activations only requires 2.7% extra flops, basically, to recompute them.
And with the selective recomputation, even the training latent throughput was higher, right? By 3%.
Uh, the throughput was higher by 30%. Yeah.
40%. Okay.
Yeah, but that's
Okay.
again, it's compared to the 30% is compared to full recomputation.
Yeah, yeah. Different baselines.
Yeah, so it's still
Mm.
slightly slower. Yeah, it's different, slightly slower than if you didn't recompute anything.
Oh, okay. It is still slightly slower, but why? So wouldn't don't you have like no less communication?
Well, you're still recomputing stuff, right? So in your forward pass, sorry, for your backward pass, it's just fundamentally faster if you can just directly go compute your gradients without stopping to recompute anything. Um, they just chose to recompute only the layers which take a ton of activation memory and require very little computation. So there is a little bit extra computation. It's like slightly slower, but you get a huge amount of memory savings, so you can train much larger models.
Okay,
Yeah, and that's how they get like a 1 trillion parameter model here.
I see.
Yeah, because
Is that
previously
how
the reason why
Python also?
they're using this baseline here because previously to train this 1 trillion parameter model at all, they had to use full AC and recompute everything. So that's why they're using it
I
as the
see.
base. So that's why they're calling it a speed up because It's not, it doesn't make sense to like, use a baseline that's not even physically possible at the time of just not recomputing, right?
Yeah, yeah. Either you do full recompute or so that's why like they would that means to save the memory to fit the model, they would have to do full recompute. So that's why they're using that as a baseline.
Exactly. And that's why the title of the paper ended up being Reducing Activation Recomputation in Large Models. Because in these large models, they had to do full AC and pay this 39% computational overhead and slow down training. And so they're
Right.
like, is there a way to do this more intelligently?
Yeah, yeah. Because I think yeah, even if you fit it, you might end up with a like in just cost terms, 39% longer runtime. Yeah, and that might eat into your gains.
Yep.
Yeah.
So they
But
combine.
then
Go ahead.
yeah, no. So I was gonna ask, like, is Torch Titan using the same ratio or
Um, well, I mean, they're not actually using the ratio. They just like this is they for each model. So this is Llama 3. They
yeah,
don't have any kind of heuristic. They just know because Llama 3 has, like, if you look in the init here, there's the
yeah,
8B, 70B, and 405B. They actually apply the same tensor parallel strategy to all of these, right? So if you look at parallelize and you go to apply TP, they
yeah,
just, for all these models, they just know because of the architecture and the number of attention heads, and I assume because that formula that we looked at, like the 5 AS over H or whatever is greater than 34, that it
right,
makes
yeah,
sense to do norm. But then also,
exactly.
but this is just for the TP. There's also apply AC, right?
Uh-huh.
And here there's different strategies. There's full selective, which is kind of like what we talked about. And for full, that's what we talked about, full recomputation. Selective is actually a little bit tricky. They have a predefined list of let's see if they have a predefined list of ops. They say it's actually not the same. The AC is not the same as what they did in actually, it's slightly the same. There's one difference, and that's for low precision training. Let me find it really quick. Selective activation checkpointing context function. Click selective. Here it is. Um, where is it? Create. Where is I know the variable name. I'll just yeah. Here it is. So here's where they create the policy for passing into the selective activation checkpoint APIs. And the policy basically says if the func, the like PyTorch operator, is not in the save list, then you save it. And so we say, okay, what is in the save list? And you look here, and what they are saving is the outputs of matmols and different scale dot product flash attention and efficient attention, so the attention layers basically. And so basically, actually, this is not aligned with the paper, right? Because they are saving the attention
Yeah,
output. But hold on, actually, now that I think about it, no, this might still align because these are only the outputs of the actual attention layer. It's not all the intermediate activations. And the intermediate activations they were talking about in the paper that take a while to that take a lot of memory but are easy to recompute are these like QK transpose, softmax dropout, attention over V. So these are the intermediate activations within the attention layer. And so this makes actually make sense because we're storing the output of the layer and to compute the gradients to continue backprop through to the previous layer, we're going to have to recompute the QK transpose, the softmax dropout, etc., to link
uh-huh.
up the layer output with the previous input, right? Um,
Yeah.
but actually, hold on, A10MM is matmul and QK transpose is a matmul, so it seems like they're saving that. So they don't. I don't think they're exactly implementing this part. Um, and then for Max, they're saving that because that's for low precision training, like float 8. Basically, you have to compute a scaling factor for a tensor, and that involves taking like the absolute max and then dividing that by the largest representable value in that data type, and then that's your scaling factor to get from you know the max value in that data or some value in the lower dynamic range to then scale back to get to your original actual values, or to do the opposite, to get from the original values to the scaled down FPA values. And this requires communication like between blocks. Like, you can do row-wise scaling or tensor-wise scaling, but like if you have a massive tensor and you need to compute the absolute max of the whole thing, usually there's Triton kernels which will compute like a local max and then do a reduction of all the local maxes to get a global max, which is like two different kernels, or they have a atomic max. So all these different Triton kernels, all these little thread blocks have to synchronize, like, and are trying to avoid race conditions by updating some global max value using an atomic max. So saving this is favorable, so you can avoid all that again. But anyways, yeah, I don't know. I don't think this is just looking at this. I don't think this is exactly. I think it's similar, but it's not exactly the same. Um, yeah, I've actually found, fun fact, there's been a lot of bugs in this SAC implementation. There's been two so far that I've fixed. That's like part of what this is doing, and there's like a different one that I fixed. Um, I think I did it. Wow. Okay, a lot of PRs just got merged. Yeah, this one. Don't say reduce scatter for SAC. Anyways, yeah, cool. That was a lot of content today, and good discussion at the end. All right,
Yeah.
anything else?
I look forward to the next one. Yeah, the next one's gonna be about where you're saying like point to point communication,
Async
breaking
TP.
down.
Yeah,
Okay. Okay.
that's what I'm working on here. And it's really interesting because it's at the intersection of the compiler and very low level uh, networking in the GPU that does not. It's like lower level than nickel, right? So it's basically
Okay.
the idea is that they're decomposing things like one all reduce
All
operation.
others.
Yeah, they
Yeah.
decompose it into like separate P2P operations and try to do so. There's actually a blog post. So basically, I'll show you. There's a blog post that kind of summarizes it nicely with some diagrams. That's like a good intro. Except for some reason the image is broke. I need to ask somebody about this. I don't know what's going on, but um, here's the blog post, and I'll probably gonna post these soon. I'm gonna get them ready to copy and paste. But um, and then here's the other one. It's called Symmetric Memory API, and this one is really crazy because it's basically like a Python API to allow people to use. Basically, the way they sell it is like Triton for NVLink collectives, right? So Triton is like the Python API that allows you to get away from these like gnarly C++ like CUDA,
Yeah.
Cutlass stuff to do
Yeah.
kernel
It's
writing.
like palette. It's palette equivalent.
Yeah, exactly. And then if you want to do, if you want to start programming like custom collectives rather than custom kernels, right? If you want to do, because the Triton handles the computation part, but then what about the communication? If you want some
The communication.
special, yeah, custom implementation of how you do collectives, then this offers like a Python API, a PyTorch-based API to do so. And it's pretty interesting actually. This blog post isn't. I didn't understand this specific diagram, but everything else was pretty clear. Um, but anyways,
Yeah.
like in the paper, it's actually really cool. The paper is from Google, and they implement async TP in the XLA compiler, I believe. Like, so the
Yeah.
compiler like automatically detects regions of the graph that would benefit, like a tensor parallel region of the graph that would benefit from basically like fusing that region of the graph into one fused node, which is then implemented via these more like these decomposed P2P operations and things like that, and then are recombined afterwards. And so basically, there's now a PyTorch implementation of this as well, but I think XLA actually did it first in the
Oh, I see.
paper. Yeah, so I
Okay.
haven't read the paper yet, but that's what it is. They
Well,
mention
that's
it.
good. That's good.
Yeah, they mention it here. This one, Wang et al. Yeah. Um, yeah.
Yeah,
So
send
yeah,
it to me.
yeah. I'll post it in here. Cool. All right. I will end the recording. Still have it going. All right.